In this chapter, we are going to talk about the data structures behind databases. So this chapter is totally optional. If you are not interested in the underlying data structures, B trees and B plus trees, then feel free to skip the following lectures. Okay, so the first question is that how the database engine is going to store the database tables. So databases are stored as simple files on the external memory, so on the hard drive disk. The concrete implementation depends on the database engine itself. So in one of the previous lectures, we have been talking about the two main types of MySQL database engines, MyISM and InnoDB. MyISM creates separate files for each database table. So whenever we create a new database table, then a new file is going to be created. On the other hand, InnoDB uses just a single file. So databases are basically simple files stored on the external memory. Okay, so for example, we have a database table with names and IDs as primary keys. This is what we have been talking about in one of the previous lectures, that the items of a database table are not necessarily stored in order. So as you can see, the first row has the primary key 1, the next row has the primary key 6, then there's an empty row, then we have a row with primary key 3, then 8, 5, then again there are several empty rows and so on. So it is absolutely crucial that the database table is stored on the external memory and the rows are not ordered by default. So there may be gaps in the table because of previous remove and update operations. Okay, and what's extremely crucial, that the external memory, so the hard drive disk, and the main memory, so the internal memory, are not independent of each other. The data located on the hard drive disk cannot be processed explicitly. And of course, because the database is located on the external memory, it means that we are not able to process the data explicitly. It must be brought into the main memory. By the way, this procedure is called paging, when the operating system fetches a given data chunk from external memory and brings it to the internal memory. In the internal memory, we can use either the stack memory or the heap memory in order to store the given data. What's crucial, that we can manipulate, so read or write the blocks or pages exclusively when dealing with external memory. So for example, we are not able to read just 10 bytes or 5 bytes or 18 bytes. If we are dealing with the external memory, we can manipulate blocks or so-called pages exclusively. The page size ranges from 2 to 16 kilobytes. So it is absolutely crucial that if we are dealing with the main memory, then we can manipulate data without any issues. If we are dealing with external memory, then we have no other option but to deal with blocks or pages. And of course, the size of these chunks ranges from 2 to 16 kilobytes or even 32 kilobytes. So it depends on the underlying operating system. And of course, accessing the blocks, so basically manipulating the external memory, is way slower than manipulating the main memory. So this is what we have been talking about in one of the previous lectures as well, that accessing items on external memory takes approximately 12 milliseconds, while on the other hand, accessing the main memory, so the RAM, takes 0.0001 milliseconds. So as you can see, there's a significant difference as far as access times are concerned. So if we have a database table like this, Adam, Kevin, then an empty row, then we have Anna, Michael and Daniel, and Sophia finally, then we are not able to manipulate just a single row. This is exactly what we have been talking about, that we have to deal with pages. So we can manipulate the blocks or the pages exclusively, ranging from 2 to 16 kilobytes. So for example, just for demonstration purposes, let's assume that 3 rows of the database table form a given page. Then, whenever we fetch a given page from external memory and bring it to the internal memory, then we are dealing with 3 rows. So we have the first 3 rows as the first page, then we have the next 3 rows as the second page, then we have the next 3 rows as the third page, and so on. And what happens to the pages in the main memory? Of course, we have to consider the items in the pages one by one. So it is the so-called sequential search, but it is in the main memory, so it is quite fast. So this is what's going to happen. If we search for a given item in a database table, then we have no other option but to partition the original database table into pages. In our example, just for demonstration purposes, we assume that 3 rows form a given page. So the operating system fetches 3 rows into the main memory, and then we can process those given database rows. For example, we are looking for a given name, then we search for that given name sequentially. Then we come to the conclusion that given page doesn't contain the item we are looking for. So what's going to happen? The operating system is going to fetch the next page with the next 3 rows from the database table. And when it is in the main memory, again we have to consider the items one by one until we find the item we are looking for. So for example, if we are looking for Sophia, then the operating system has to fetch 3 pages, the first page, the second page, and the third page containing the name we are looking for. Okay, so if we have a query like this, we select every column from the city database table where the code is equals to the United States of America, what's going to happen? If we are looking for an item, for example, we are looking for cities where the country code is equals to the USA, then we have no other option but to consider the entries one by one. So what's going to happen? The operating system fetches the database table content into the main memory, of course, as far as pages are concerned, so the first page, second page, third page, and so on, and we have no other option but to consider every single entry one by one. And of course, this is called linear search with ordo and linear running time complexity. So a good question that is it a good approach? Of course not. We can do better if we keep that underlying data in a sorted order. So we can apply binary search, which means that we can reduce the linear running time complexity to logarithmic running time complexity, which is way faster. So what is the solution? We should keep the database table sorted according to the primary key, for example, and this is how we can achieve logarithmic running time complexity. And this is why we have to talk about B trees and B plus trees, because these tree-like data structures do exactly what we have been talking about. They store the primary keys, so basically the indices, in a sorted order in a tree-like structure. So this is what we are going to talk about in the next lecture. Thanks for watching. In the previous lecture, we have been talking about external memory, and in this lecture, we are going to focus on B-tree data structure. So we know that tree data structures can guarantee logarithmic running time complexity because they store the items in a sorted order. So this is what we have been talking about in the previous lecture, that if the items are unsorted, then we have no other option but to consider every single item in the database table on a one-by-one basis until we find the item we are looking for. Can we do better? Of course, if we store the items in a sorted order, for example, in a tree-like data structure. So we can store the indices, such as the primary keys of the database table, in a B tree. Okay, so B trees are very similar to binary search trees. So there are nodes in the given tree-like structure with given values. These are the indices. So 12 is going to represent a given row in the database with primary key 12. 4 is going to represent another row in the database table with primary key value 4, and so on. So we store the primary keys or the indices in a tree-like structure like this, and every single node in the tree stores a pointer to a database table's row as well. So for example, like this, if we have a database table with name and the primary key as far as the IDs are concerned, then we can construct a tree-like structure out of the primary keys 1, 6, 8, and 5. So as you can see, the tree-like structure is going to contain the indices 6, 5, 8, and 1, and every single key, so basically every single node of the B tree, is pointing to a given memory location as far as a given row of the database table is concerned. So this is how we can construct a tree-like structure out of the indices or the primary keys. And then if we are looking for a given row in the database table, then what do we have to do? We have to search for the primary key in the tree-like data structure, and if we find the primary key we are looking for, then we just have to follow the pointer in order to find the database table row. Okay, so for example, we are looking for a database table row where the primary key is equals to 9. What do we have to do? We have to start with the root node, because usually when dealing with tree-like data structures, we have access to the root node exclusively. If you are interested in the concrete implementation of binary search trees, B trees or B plus trees, then take a look at my other course on algorithms and data structures. So anyways, we start with the root node, and because we are looking for 9 and 9 is smaller than 12, we have to visit the left child, and this is how we can discard approximately half of the data set in every single iteration. And basically this is the concept behind binary search, and this is why we can end up with logarithmic running time complexity. So 9 is smaller than 12, so we visit the left child. 9 is greater than 4, so we visit the right child. 9 is greater than 8, so we visit the right child, and this is the value we are looking for. So as you can see, in a binary search tree like this, the right subtree is always contains items that are greater than the actual node. The left subtree contains items that are smaller than the actual node. So if we consider the root node, for example, then it is true. If we consider 8, then the left child is smaller than the given node, the right child is greater than the given node. So this is how we can store the items in a sorted order. And we have found the item we are looking for. Of course, a good question that is it a good solution to store the primary keys in a binary search tree like this? Unfortunately, no. The problem is that we have to swap pages every time we visit a child node. So whenever we start with the root node, then the operating system is going to fetch a page into the internal memory. Then we come to the conclusion that we have to visit the left child. Then again, the operating system is going to fetch another page into the main memory. Then again and again. Because this is what we have been talking about, that as far as the external memory is concerned, we can manipulate, so read or write the blocks or the pages exclusively, where the size of the pages range from 2 to 16 kilobytes. So we are not able to manipulate just a small portion of data, we have to deal with blocks or pages. And this is why this approach is not efficient, because every time we visit a given child, we have to deal with another page. The operating system is going to fetch a huge amount of data into the internal memory and so on. So what can be the solution? The B trees store multiple keys in the same tree node in order to minimize page swapping. So what does it mean? If we store 3 values in a node, then what's going to happen? Whenever the operating system fetches a given node into the internal memory, we are not going to deal with a single key value, but we are dealing with multiple values. And basically, in a database related tree-like data structure, there may be hundreds or even thousands of values associated with a single node in the tree-like structure. So the nodes contain multiple keys, and these will be fetched into the main memory, and we search for the item we are looking for in the main memory. So every time the operating system fetches a given node into the main memory, then of course there may be multiple values. So we have to consider these values one by one in the main memory. So we have to consider 8, then 12 and 20 until we find the item we are looking for. So far so good. We have managed to end up with a tree-like structure, and we have managed to solve the problem regarding the external memory. So we know for certain that we have to deal with multiple key values because the external memory operating on blocks or pages, but of course there are some disadvantages of using B trees. So first of all, we have to store the pointers to the database rows with every single key in the tree-like structure, and this is not that efficient. So for example, 8 as the key is going to store a reference reference to the database table row. Then 12 is going to store another pointer to the database row. Then 20 is going to store a reference to a database row, and so on. So every single key is going to store a pointer to the database table row, and it is not that efficient. We can do better with B plus trees. Okay, and another disadvantage for B trees is that the operations are quite complicated, such as inserting or removing items from the tree-like structure. So for example, if we want to insert a given value into a node that is already full, then we have to split the original node into two, and it may happen that we have to delegate a given value up to the parent node, and of course it may happen that we have to split the parent node into two halves as well, and then we have to delegate the middle value to the parent node, and so on. So it is quite complicated to implement a B tree from scratch, as far as insertion and as far as the remove operation is concerned. So this is why we can do a bit better if we are using B plus trees, and this is exactly why we are going to talk about B plus trees in the next lecture. Thanks for watching. In the previous lecture we have been talking about B trees. We came to the conclusion that it is working absolutely fine, but there are several disadvantages, and this is exactly why B plus trees are a bit more efficient data structures as far as database management systems are concerned. Okay, so first of all, B plus trees are very similar to B trees, but there may be duplicate values. What's crucial that the leaf nodes contain all the values, and this is why there are duplicates. The leaf nodes form a linked list, which is a crucial feature when dealing with databases, and we can store more keys in the nodes because no need to store the pointers to the database table related rows. And finally, it is more easier to insert and remove items. Okay, so let's take a look at the topology of a B plus tree. So as you can see, again, it is a tree-like structure. We have a root node, we have left and right childs. There may be several keys in a given node. Okay, and as you can see, the leaf nodes are going to contain all the values in the data structure. So in this case, we have 8, we have 5, we have 12, and these values are also present as far as the leaf nodes are concerned. So we have 5 again, 8 again, and 12 again. So you may pose the question, then why do we need to use these duplicate values? Because this is how we can store the data in a sorted order. So for example, if we are looking for the value 1, then we start with the root node, and we know for certain that 1 is smaller than 8, so we go to the left child. And this is how we have eliminated approximately half of the data structure. Then 1 is smaller than 5, so we keep going to the left, and then we have to consider just 3 items, 0, 1, and 5, and this is how we can find the item we are looking for with the help of binary search basically. So we keep the data in a sorted order, but as you can see, all the items are present as far as the leaf nodes are concerned. What's absolutely crucial that only the leaf nodes store a pointer to the database table related rows. So for example, if we have a database table with Adam, Kevin, Anna, Sophia, Michael, and Daniel, as you can see, the leaf nodes store a pointer to these database rows exclusively. The root node or the middle nodes have no pointers at all. So as you can see, the 0 is pointing to the first row of the database table. 1 is pointing to a row in the database table where the primary key is equals to 1. And again, it is absolutely crucial that the database table is not sorted by default. We use pointers in order to get the given row in a database table, and as you can see, a B plus tree contains every single value in the leaf nodes. So the leaf nodes are the nodes that store pointers exclusively, and what's absolutely crucial that the leaf nodes are pointing to the next leaf node in the B plus tree. So basically the last layer of the tree-like structure is a simple linked list. Why is it good? Because if we want to select everything from a database table, then what do we have to do? We have to look for the leftmost item, and then we have to consider all the items. So basically we have to visit the right neighbor, and we have to follow the linked list pointers if necessary. So 0, 1, 5, 6, 8, 12, 13, and 17. So this is how we can get every single item from a database table. What if we would like to select every column from a city database table where the ID is between 6 and 12? It is going to be quite efficient and quite a fast operation when dealing with B+ trees. First, we have to look for the ID 6. So 6 is smaller than 8, we go to the left. 6 is greater than 5, so we go to the right. And then we have to consider all the items until we hit the value 12. So 6, 8, and we have 12. So these are the primary keys that form the result of this SQL query. So it is absolutely crucial that the results of SQL query are going to be leaf nodes no matter what. So we store every single primary key or every single index as far as the last layer, so the leaf nodes are concerned. We just use internal nodes and the root node to be able to use binary search. So to be able to discard approximately half of the data set in every single decision when looking for a given item. Okay, so let's compare B trees and B+ trees. As far as B trees are concerned, all the nodes have pointers to database table rows, while on the other hand, as far as B+ trees are concerned, just the leaf nodes have pointers to the table rows exclusively. There are no duplicate values in B trees, but there is a redundancy because of the leaf nodes as far as B+ trees are concerned. All the operations are quite complicated and a bit slower when dealing with B trees. On the other hand, as far as B+ trees are concerned, there are easy and fast operations. So, as far as most of the database servers are concerned, such as MySQL, it relies heavily on B+ trees. So this is the data structure under the hood, and this is why we can execute the SQL queries quite efficiently and quite fast. So that's all about the data structures behind MySQL databases. If you are interested in the concrete implementation of tree-like structures, then take a look at my other courses on algorithms and data structures. So that's all about B+ trees. Thanks for watching.